Alrighty, hey everyone, Rusty Rob here. Welcome to the video, and yeah, welcome to the studio, which is just a little studio at work, which I thought I'd give a try. Today I'll be taking you through one of the Kickstart problems from the weekend, which was pretty interesting, the pizza delivery one. So without further ado, let's get into that. Alrighty, so I'll link to this problem in the description so you can read through it yourself. But essentially you want to deliver some pizzas. So yeah, give it a try if you haven't tried solving it already. But you start off at a restaurant, basically, somewhere on a grid. So it's like a 10 by 10 grid kind of thing. And you got 20 minutes to get as many coins as possible. So how many coins can you get after 20 minutes? And you got to print that out, or print out impossible if it's not possible to deliver all the pizzas. We've got about 10 customers, various places on the grid. We've got to deliver some pizzas to them. Each customer, there's a cost associated with each pizza delivery, and there's also all these tolls at each intersection. So these tolls, they're going to toll you based on how many coins you're carrying. So typically if you've got a lot of coins, they're going to try to tax you more. But sometimes it might be it really depends on how many coins you got and the operator function. So you got these various operations. So maybe going down, it might be the number of coins you have plus 4, or if you're going to the west, it might be like the number of coins you have multiplied by 3. And if you're going to the east, maybe it's how many coins you have divided by 4. And the integer division is towards negative infinity. It's not towards 0. You'll see that in a bit. Anyway, so yeah, that's the problem. You don't necessarily have to deliver a pizza. So in this case, it's actually better to not deliver this customer a pizza, to go down and then go back up and then deliver their pizza. And that just works out to be cheaper, because then you have less. I guess you have less coins at this toll booth here. So maybe you get taxed less or something. I'm not sure. You get, and then you deliver this customer's pizza after that. They have explanations for the solutions. Anyway, let's just go to the Rust code. I think that's why we're here. So yeah, it's reasonably straightforward. Well, I mean, it's pretty complicated, but it's reasonably short, is what I should say. This is the gist of the solution here. So we're using DP. So I'll mostly just go through this code. But yeah, here's some code that just kind of goes through the input and does a little bit of formatting. I'll put this on GitHub and link to it in the description. But essentially just storing the tolls as a tuple with the operator, which is like multiplication or division or whatever, and the constant, which is an I64. And then I'm just formatting the customer locations a little bit. So I'm taking the IJ coordinate of the customer and their cost of their pizza delivery, and I'm just, at each coordinate, I'm just storing the customer ID, and I'm storing the cost in a cost array. And this is just nice, because then I can look at a coordinate later and be like, is there a customer here that needs a pizza? Okay. And if I know the customer ID, I can use that in a bit mask. So I can use a bit mask to keep track of all the pizzas delivered. And you'll see that here. So our DP is from starting with time, and then it's using the pizza state, which is starting at 0 and working its way towards having all the pizzas delivered. So it's just a bit mask. And then it's an IJ coordinate. And at each point in our state, we have some cost, because not every state is possible. So then the solution for that is just none. Whereas if it is possible, we have some cost, which is like the maximum amount of coins we can get at that state. And so yeah, we're just gonna initialize everything to none, and then set the initial position to some cost of 0, because we start off with 0 coins. And then we're iterating through every single state, and we're just saying, from this state, is it possible to even be at this state? If it is possible, what is the most number of coins we can have at this state as calculated previously, because we're using dynamic programming, which, you just assume you have a value and then you make sure you calculate all the values at one step into the future. So one step into the future will be just t plus 1, right? So the next point in time, and potentially one step into the future, but also potentially we're adding a pizza to our list of delivered pizzas, because maybe at the next step in time we'll be at a customer that has a pizza and we're going to deliver their pizza because we haven't delivered it already. So let's have a look at that. So at a particular state, how do we get to the next state? How do we make sure that from our state getting to the next state makes sense, that that's the best cost for that state? Maybe it's better to get to that state from a different state. So first, what are the states possible from here? Well, we've got this neighbors function, which from our IJ location and our current number of coins and tolls, it can work out, okay, you can go up or you can go left or you can stay where you are. And so for each of those movements, here's your new location, here's your new number of coins after applying the toll. And then, so we'll have a DP. And we'll just, for that new location and new state, we're going to just set it to the maximum here. And this is quite cool actually, because this value could potentially be none, right? Maybe we've never been to that particular state before. And the maximum of none and any value is going to be that value, because none is less than negative infinity in Rust. Rust has various traits called partial ordering and things like that. It guarantees ordering on anything that can be compared. So we know this is going to work. It won't work if we're wanting to do the minimum, but for the maximum it's going to work. So none is less than, we're using I64s in this case. So that's cool. So it just makes our code clean. There's some little tricks you can do for doing the minimum as well, but we won't get into that. And so, cool. So this is setting the maximum for one step into the future if we're not delivering a pizza for that particular neighbor. But what if there's a customer at that particular position? Then we also have the option of deciding, do we want to deliver that pizza or not? So if there is a customer ID there, then we're going to check our pizzas, which is something like this potentially. So we bit shift that to get that customer's bit into the 1 position, and then we do an intersection with 1, and that's saying, okay, is that customer's bit set or not? If it's 0, then that hasn't been set yet, right? So okay, we haven't delivered their pizza yet, so we can deliver it. I mean, we get a lot of coins if we could just deliver infinite pizzas to one customer, right? So yeah, in that case, we're still going one step into the future, but now we're adding that pizza to our state as well. And yeah, once again, that state will just take the maximum of its current value and the new cost, which is equal to, the cost is basically our current number of coins set plus the toll, that's what our C2 cost is, right? Plus the cost of delivering that pizza. And at the end we're just delivering, so we're looking at, okay, after m minutes, and this is just this bit mask here, right? So when all the pizzas are delivered, that gives us a matrix of ij coordinate, this gives us an n by n matrix of 100 values. So we're just going to iterate through those rows, and now we've got one iterator over all of the optional references to I64 values. So it's going to be by reference because we're using iter. So we're just borrowing this. And we flatten that. So when we flatten that, that's when we get one iterator of all of the optional I64 references. And we flatten that again. And when you flatten an optional value, you just either get the value or you don't get anything. So now we've just got all the I64 references. We're going to clone that, which means we're getting the value instead of the reference. And these are all zero cost abstractions in Rust, which is good. And then we're taking the max if it exists, right? So potentially there's no valid ways of delivering all the pizzas. So this might be none, or it might be some I64, which is the maximum. And yeah, then we just print impossible if this is none. And yeah, that's it. Our neighbors functions, just looking at the different directions, calculating the toll, returning the new position and the toll cost, which is and that's just using a match statement. So we don't actually need to set this. We can just go like this, a bit cleaner. So we're returning, so based on the operator, which is the first value in the tuple, we'll use our current number of coins and the constant, which is the second value in the tuple, which is used to calculate our toll. And then this is the only complication is in Rust division, I think, is towards 0. So and they want towards negative infinity. And the reason for that is you want the tolls to be like monotonically increasing or something like that. So you don't want like negative cycles or something, because then pathfinding kind of breaks, and then you need to kind of brute force the solution, which would probably not work in the time limit. And let's see the cost of this, right? So we're just essentially setting this and iterating through it all, right? So it's going to be, so for time is up to 20, and then we have the pizza states, which is 2 to the power of 10. Oops, if I can type. And then we've got, what do we have next? We've got I going from 0 to 10, and then we've got J going from 0 to 10. And then we've got 100 test cases. So that's the number of operations, so about 200 million. Yeah, and then Rust, that'll take, maybe a second or so. But when I submitted it, I think it took about 6 or 7 seconds to run, but that's mostly just waiting for it to get to the front of the queue in the CodeJam system. So yeah, I hope you all gave this problem a try, or if not, you're going to give it a try. It's quite fun. Quite a fun one, and I think coming up with this DP structure is quite important, because it just helps you reason about the time complexity and space complexity, and although this is a lot of for loops, you can just think of it, okay, we've got one state, we're just generating a future state, and that makes this code a lot easier to reason about, I think. And yeah, then you got like the bit masks and things like that, which is quite a cool technique for iterating through all possible pizzas, right? So this is giving us every possible bit set from no pizzas to all the pizzas. And I guess you could do a bit of pruning here, but I don't think it'll make much difference. Like, I mean, if the time is 3, there's no way of setting 10 pizzas after just 3 minutes, kind of thing. Yeah, cool. Well, thanks for watching. Next video, I think, will be on, there's a really difficult meta hacker cup problem that I might do next. And there was like an n log n solution for that, where people were using like, what is it called? Heavy light tree decomposition. So it's like a decomposition of a graph, and like applying Dijkstra's and stuff to calculate some optimization across a tree. But I found a order n solution with like kind of came up with a new algorithm, which is pretty cool. So be on the lookout for that. And yeah, if you're doing Meta Hacker Cup this week, I'll see you there. I think qualifications in a few days. Alrighty.